want to apologize for starting a bit late, but we were waiting for other attendees to come and join us. So we're in a good state now to start. So before I start, let me introduce myself. My name is Ajay Katyal. I'm the Business Development Manager for Honeywell Refrigerant Business. I'm based out of Dubai office. And I will want to thank AG Chem, Mr. Akmal and his team for actually organizing this for us, for giving us this platform to come and talk about the new low GWP refrigerants. And I must assure you, it's not just a discussion about refrigerants, but the whole how the technology shift is happening in the air conditioning field, given these regulations are coming on to us. But before I do that, I want to introduce the Honeywell team who's here with us. We have Amanda Joshi. She is the General Manager of the Global Business. And then we have Amir Naqvi. He's the General Manager for our Middle East and Africa business. He's based out of Dubai and Saudi. And then we have Nick Rother. He's the Sales Manager for Middle East and Africa. Then we have Rushan. Maybe he's just going out to take his coffee. Rushan, he's our Sales Manager for Turkey. And then the man standing behind, Mohammad Lashin, he is the sales manager based out of Cairo. He manages the market and he does little more than just managing the market for us here. Before I start, I just want to invite Amanda, if you could just say a few words and then we can start.
So good morning, everyone, and a very warm welcome. My name is Amanda Joshi. I'm normally located in the US, in New Jersey, but I love to visit this region several times per year, and just wanted to say thank you all for coming out and for joining us in this very important discussion. Honeywell has been at the forefront of inventing HFCs and then continuing research on how to reduce global warming potential while not sacrificing energy consumption. So it's really important for us, especially in the discussion today, to let you know we're here to support all the transitions that are coming. We have a very big thank you to AG Chem. They're a very strong partner of ours, and we're looking to continue to develop and grow. They've done amazing things in the market here, and they're at the forefront of probably all of the refrigerant business that I've seen. So thank you so much also for organizing and putting this together. And we look forward, especially if there's new ideas for projects or how we can work together. Honeywell does a lot of things to field test all of the refrigerants and gather data, but wherever we have opportunity to have third parties come in and work with us and do additional projects and help us validate the things that we see, we very much appreciate it. So thank you so much. I'm going to hand it back over to Ajay and just say thanks for joining us, and I hope you enjoy the session this morning. Thank you so much.
And now, when we start, I don't think this man needs any introduction, but we have the stalwart of, I dare I say, not just Egyptian air conditioning industry, but the Middle Eastern air conditioning amongst us. Dr. Al-Alama is here with us. It's my pleasure to introduce him. It's my pleasure to invite him to the dais. And Dr. Al-Alama will share whatever work in the region he has done, especially under Praha and AG Praha, and take us through how he sees that Egyptian air conditioning market can evolve with these changes which are happening in the industry. So over to you, sir.
Thank you very much indeed. صباح الخير، اهلا وسهلا. انا لقيت يعني مناسبه جيده اني اتكلم مع حضراتكم شويه على وسائط التبريد الجديده. I'd like first to thank AG Chem for their gracious invitation to ask me to come and invite here. I see old friends here, and I welcome seeing them again. I see new friends, I hope, from the leadership of Honeywell, and I extend my thanks to all of you. If we are going to talk about refrigerants in Egypt, we have to talk about a project that we've done starting 2018, which is AGPRA. This project was aimed at choosing new refrigerants that have lower global warming potential. So I thought I'd talk about this, and then I moved to the repercussion of this project into writing the codes of refrigerant, the first code of refrigerant for Egypt. And then thirdly, I'll talk about what are the refrigerants, that are now possible to use for chillers, heat pumps, and so on and so forth. And the third item is really a very long item that will take possibly a couple of hours. So I thought I'll just skip over it and give you an idea of where the market is going. Because this is a question that we are always asked. Okay, we are not supposed to use 410A, we are not supposed to use R22. What are we supposed to use for chillers? Medium pressure chiller, low pressure chiller, medium pressure chiller, high pressure chillers. What are the overview of refrigerant? So this is what I'm going to talk about very quickly. I'm not going to take all the time, maybe perhaps 15, 20 minutes, just to put you in the mood to listen to Honeywell, if you permit. Right. So those are the content, as I said, AGPRA, Honeywell contribution to AGPRA. I must here thank Honeywell for their copious and very generous contribution with refrigerants, technology, and equipment during AGPRA. And I'll state exactly what they've done. And the Egyptian Refrigerants Code, and then the UN Technology and Economic Assessment Panel, which is TEEP, assessment report of 2022 on the refrigerant for the industry. Right? Now, AGPRA was a tailor-made program to test 4 types of refrigerant for R22, it's actually 3 compared to R22, and other 3 compared to R410A. What we asked the industry to do, 6 OEMs, is to build prototype, specially made for those refrigerants, and then to compare their efficiency and their refrigeration capacity with either R22 or R410A. So in total, we tested 43 different units. And the tests were made at the manufacturers themselves, labs, a witness test. And in the end, we made 164 different tests. So it was a very extended test that took about 2 years. And I think it was very useful. And although we looked at Praha, which was the same test but done for the Gulf region countries, although we looked at Praha as a role model, our program was much more useful than Praha and actually yielded result in the end, while Praha got a bit stuck in the end. So we are very proud about that. I was the technical consultant for the project, and until today I'm still asked about it, so it's still ongoing. And we are hoping that we are going to do a part 2 of this program next year. Okay. Can you make it a bit bigger?
Okay.
Yeah. Can you see that? All right. So we tested R290, R32, Arkema R20D. Now it has an R number, but at the time of the testing it didn't. And DuPont DR3, DuPont DR5, and Honeywell R444B. It used to be called L20, and then it got an R number, it became R444B. And Honeywell L41, which is R447A. Against base units R22 or base unit R410A. At the time, we tested 12,000 BTUs unit, split unit, 18,000, 24,000, and central unit, 120,000 BTUs, central unit. And one of those units, using Honeywell refrigerant, was tested with a microchannel condenser. Okay. Now, if we look at all the refrigerants that we tested, the alternative to R22 were R290, a hydrocarbon refrigerant, very low global warming potential, when you compare the 100-year list of the RTOC, an H3 refrigerant, but flammable, of course. And we tested R444B, the Honeywell refrigerant. It's an A to L refrigerant classification, so it has some flammability. And the GWP was 310. And we tested also R454C, a Chemour ex DuPont chiller. It's an A to L refrigerant, and the GWP is 295. And then R457A, an Arkema refrigerant, an A to L again refrigerant with 251 GWP. So those were the refrigerant we tested as alternatives to R22. Regarding alternatives to 410A, we tested R32, R447, a Honeywell refrigerant, R454B, a Chem refrigerant, and R459A, an Arkema refrigerant. Those refrigerants were tested at Miraco, and we have here Engineer Yasser with us, and were tested also at Power, at Volta, and at SAS, at all the manufacturers that were at Unionair, the manufacturers that were interested to do the test. And it was all tested against base unit, either R22 or R410A. Now, in the end, the refrigerant were very useful. The result was very useful in choosing 2 or 3 refrigerants that we can use in the future as a transition refrigerant until we go to a lower GWP refrigerant. At the time, the alternative refrigerant 410A for Honeywell was chosen, 447A, with a GWP of 600, a bit high, but lower than Daikin R32, and the results were really very good for both refrigerants. But we sort of forgot about the alternatives to R22 because the components themselves were not available. And we looked at alternative to 410A because they are more available. So this is the refrigerant that we tested, and it produced very good result. If you want to see all the refrigerant results, that are available at the UNEP site under promotion of low GWP refrigerant for the Egyptian air conditioning industry, 2018. Thank you. Now, let me go to the result that we got out of those. We wrote a code for the first time, an Egyptian code for a refrigerant because of the process that we went through to do EGPRA. And the code consists of الباب الأول الالتزامات الدولية والوطنية ذات العلاقة. الباب الثاني توصيفات وتوصيف وتصنيف وسائط التبريد. الباب الثالث وسائط التبريد قابلة للاشتعال. Chapter number 3, which is refrigerants that are flammable, we got a lot of question about it. Why didn't you choose refrigerants that are flammable? Why do you go to A to L refrigerant? And the reason, of course, is that the actual market is not ready for refrigerants that are flammable. It's much easier to choose a flammable refrigerant as an alternative to R22. But in the end, you have to be able to solder it or keep it together with other part of the system without causing a fire. You have to be able to deal with it, with its flammability and sometimes toxicity. And this is, until today, is not available. Although it looks as if it's going to be the future, either sooner or later. But this is where we always thought that we are going to go, but we are not really there with it. So, okay. So this is chapter number 3. Chapter number 4 is اسطوانات وحاويات وسائط التبريد. Chapter number 5 معايير اختيار وسائط التبريد. And this is how to choose a refrigerant. Under what condition would you choose this refrigerant rather than that one. And then chapter 6 is متطلبات الاحتواء والاستخدام السليم لوسائط التبريد. How to handle new refrigerant. And then chapter 7 is the sort of forms that you have to fill to make sure that there is no leakage that are not recorded in the refrigerant. If you have a leak, how to deal with it. So this is very quickly the code of new refrigerant. Now I have to mention people that I worked with me in this code. Dr. Assam Khalil, the late Dr. Assam Khalil, our great friend and our great professor, Dr. Said Shibl as a sort of the guy who put us together, the late Mohandes Amin Hagazi, and we have people from Volta here. We have Muhtadi Gawadi, engineer Muhtadi Gawadi with us. It was really greatly appreciated. And Dr. Izzat was also available and gave us a lot of help. Engineer Mamdouh Abdel Qadir, Engineer Fuad Hamad, who is with us here. Engineer Fuad, here he is. And also Mohandes Muhammad Mansour, and of course, engineer, the incomparable Mohandes Ahmad Al-Orashi, who is with us here also. Very good. Now to wrap up, which refrigerant are we supposed to use when we choose new refrigerant? And very briefly, if you have a sealed domestic commercial refrigeration appliance or heat pump, that is, now a lot of work was using R134A or R404A. Of course, both of them have high GWP. So now, with the advent of the new refrigerant, there is more concentration on hydrocarbon 290. A lot of the sort of domestic refrigerators use R290 or HC290. And also, especially, this is in Article 5 country, such as Egypt. So this is really going. The other things is R477. It's also getting part of the work, but not as much as HC290. Food retail and food service refrigeration, 744 is really taking the lead now. And a lot of second refrigerant with 744, they are using HFC 134A and R450A and B513A and HFO 1234ZE and R717 and ammonia refrigerant. Heat pump, heat pump. They were using 410A, of course, and now they are moving more towards R32 and R454B. And this is one of the refrigerants that we tested in Egypt, R454B. And 290, of course. Air-to-air air conditioner, which is the majority, is using now a combination of HFC and HFO, in particular R32, R125, R134A is going out, and HFOs such as 1234YF and 1234ZE. Last, the chillers. The low pressure chillers, what is used now as a lower GWP refrigerant is R123, R123ZD, and R514A. Why? Because their GWP is 79 or 1 and 2. This is for the low pressure. The medium pressure, of course, R134A is still being used with a lower GWP refrigerant, the R513A and the R151B and the R1234ZE and 1234YF. On the high pressure side, R32 and R410A are replaced by R456A and R452B and R454B, and of course the R32, although it has a higher GWP. Thank you very much indeed.
Thank you, Dr. Anand. And before I start, let me just say, before I start, okay, that's good. There was a miss, I should rectify it. We also have with us. No, this is not for the speaker. Okay, then it's okay. Sorry. Now I realize. So yeah, before there was a miss. We also have from Honeywell, from our US headquarters, Claudia. Claudia, if you could just stand up here. She's, sorry, I just missed you there. You were busy working. And she manages channel excellence for us. And thank you very much for being here. Coming back to what we want to discuss, thank you, Dr. Allah, for setting up the stage. My idea was to take you through what are the changes which are happening and why they are happening. not talk about Kigali as much. I assume, and I think I assume it rightly, that most of us know what are the timelines, what it means for us, why that's been driven. What I wanted to talk beyond that was what exactly also the local governments are doing towards it, especially Egypt. And that's the point I want to touch when we talk about it, towards regulations, both towards energy as well as towards the emission reduction. And then I'll talk about all those options which are there. It could be sometimes confusing, but since we have had this transition, similar transition in Europe, we are in the midst of this transition in US. So there are learnings which are coming out of those. And based on those learnings, this confusion is getting cleared. The front runners for each applications are coming out very emphatically. So I'm going to talk about that. And then basically we'll touch upon a bit of performance. As Dr. Allah said, the reduction in GWP is one thing, but you cannot compromise on the performance. Actually, on the second hand, you should rather be improving it with this transition, because this transition presents us that opportunity where we can go back to the drawing board, not just talk about the refrigerant GWP, rather we talk about the whole system. So I'm not going to talk about this, we know about this, but what it is saying is this. The point which I'm trying to raise here is that this transition is coming, and it's not coming just across our industry. It's being driven, the emission reductions, that's across the board, whether it's construction industry, whether it's oil and gas, and we from HVAC industry also a big part of it. But what I want to say is that even in our region, especially if you talk about Egypt here, Egypt has committed to reduce by 1/3 of its emission, and that also driven by mainly energy efficiency. So that goes back to my previous point. While we work towards reducing our refrigerant emissions because of the lower GWP they bring, we cannot forget about the energy efficiency. And that's one of the things which HFO bring to the front fore, is that they help you reduce your GWP of the refrigerant, but because of their thermodynamic properties, they're also more energy efficient. This is the timelines. The one thing which we know our timelines, one thing which I always talk about is that Egypt being A5 Group 1 country, you may see that your timeline starts somewhere around 2030, the reduction starts under Kigali, where we're going to phase down the HFCs, the higher GWP refrigerants. But the point I want to make is that before that, the A1 countries, the European Union itself, they have already made this transition. So most of the biggest consumers of refrigerants and most of the biggest producer of refrigerants and most of the biggest producers of equipments come from these regions. Those are big, heavy regions in terms of consumption and production. If that part of the geography has moved away from lower GWP refrigerants, that means a lot of technological work will be done, new technological work will be done with lower GWP refrigerants. We wouldn't have access to existing HFC refrigerants much easier. So it's in about time that we should start planning for our transition as well. This is a bit complicated chart, but I just want to spend some time on this for us to understand. Basically what it says, this is from the UNEP Global Cooling Report, that so far in 2022 baseline, based on all the cooling equipments which are running, the emissions which they produce is around 4 billion tons. There are two components of that emission. One is the emissions because of their high GWP refrigerants running in those. When those refrigerants leak during storage, transport, or operation in equipment, that causes around 1.5 billion tons of emissions annually. And then there is the efficiency, because every equipment, AC equipment, refrigeration equipment needs energy to run. For us to produce energy, we have to burn fossil fuels. That causes emissions. So if we do not make all those changes which we are talking about it, and we just continue business as usual, we will be more than doubling up those emissions. So think about it. Whatever air conditioning industry is probably like 170 years old, 150 years old. Whatever we have done in 150 years, we're going to double it up in 25 years if we do not do anything else, if we just let the business run as usual. So it is imperative for us that we should think of doing something not just towards the lower GWP refrigerants, but also towards energy efficiency. Then there is a planned pathway which UNEP has suggested, that how can our industry reach near net zero emissions by 2050 in next 25 years. And what you can see there is, if I could highlight that, the biggest component which if you see on the orange bars, before I go there, even if we comply with Kigali fully, which we should, will bring down the reduction only by 1 billion tons. That's not even 20% of what we're going to be emitting. So we have to work towards improving energy efficiency by optimizing system design, by optimizing our refrigerant selection, by optimizing the building envelope. And that's what the path they have given. So that's the point I want to raise, that while we say that the transition to lower GWP refrigerant is imperative, and it is under Kigali, its impact is very limited if we do not consider the other aspects, mainly the performance and energy consumption. So this basically means is this: when we select our new refrigerants, it's not just driven by their first emissions, which is their GWP, it should also be driven by their energy efficiency. And of course, as Dr. Allah said, they should be safe to use. We should make those refrigerants safe to use. We should impart those trainings, and it is our, as a player of this industry, this is our responsibility also, and we take pride in doing this so that those refrigerants become easier and safer and more reliable for our industry to transition to. What it basically means in terms of emissions and energy efficiency. When we reduce our transition to lower GWP refrigerants, we are reducing our, what they call as scope 1, the direct emissions which is caused. Now, if you talk about R134A, which is the most versatile HFC refrigerant which is being used, its GWP is around 1400. Actually, that's by the latest assessment report puts it in north of 1500 GWP. That means 1 kg of R134A being released into the system, whether by leakage, whether by mishandling, is equivalent to releasing 1500 kilograms of CO2 into the environment. That's the one thing. The other thing is that, which I spoke about, was the energy efficiency. And R134A, out of its other lot, is an efficient refrigerant, but it's not the best in class anyway. The transition to HFOs, you not only reduce your GWP for some of the HFOs, the GWP is even lower than CO2 itself. Their global warming potential is much lower than the CO2 itself. That's one. As I said, most of them bring almost from somewhere around 5 to 15% energy efficiency as well into the system without other changes being done. That's basically like 5 probably for medium pressure chillers I'm talking about, 15 going into the refrigeration side of application. So that basically means that you can reduce your emissions for both scope 1, scope 2, but the scope 2 emission is one thing. If you can reduce your energy consumption, you're basically reducing your operating expenses also. So we did a study for Saudi Arabia, which is one of the biggest market in our region, and we see that if the market were to transition to HFOs, they can reduce their emissions, total emissions, and Saudi is an oil producing economy, so the emissions are much higher there, by 5%. That's the impact we can bring. Now I'm going to talk about our HFOs, that for all what applications are they available. Actually, for all the applications we can think under HVAC and R, whether it's data centers, whether it's commercial buildings, whether it's residential buildings, whether it's heating or cooling, both of those, whether it's supermarkets, food retails, you think of it and we have an application, we have a refrigerant for that. So that again shows that this technology, thanks to whatever transition has been done in the world, one, and whatever the pioneers of industry, like Dr. Allah here, most of you have done in your region, this solution, HFO solutions, have been established for all the applications. This is not something new which we are going to try. So if you want to see basically, I have tried to list all the applications including car ACs. These are the applications you can think of, whether indoor unit, outdoor, whether compression technology is screw, whether centrifugal or scroll, or even reciprocating for that matter. What are the refrigerants which are under HFC currently in use? What are their GWP? And what are the new HFO options you have? It may look a little more, but in total, they are like just 5 options. Out of this, Z is the most versatile one, but those 5 options can cover almost all the applications which I showed you in the last slide. It's not something new which we are trying to bring into the market. We bring it into our industry, stepwise into our region, though, that I agree. And I actually appreciate that you guys being here. That means you also have that drive. You want to bring that transition into our industry in Egypt. But the technology itself has matured. This is a small QR code I put in there. If you could scan it, you can actually see the whole the roadmap in much detail. If you can just scan this using your phone cameras, you can see the roadmap, what are the transition, what are the available options. I'll just keep it in the screen for like
few minutes, so you can scan it. But that's in detail, depending upon capacity, depending upon your usage, whether it's a new build, whether it's a retrofit, all those details are there if you scan this. Okay, I think I can move. Now I'll go a little deeper. I have shown you the chart where I say that our technologies are available for all the applications. But I'll go a little deeper. I have picked the comfort cooling application. I'm going to talk about not just GWP, but I'll talk about what exactly is happening given all the HFO options we have, how the market is transitioning, what we are trying to do in terms of medium pressure, low pressure refrigerant or higher pressure refrigerants. And of course, the flammability, the angle which is more critical for us to understand. So if you could just look at this chart with me. This chart on the x-axis talks about the pressure at 31 degrees. Why at 31? Because that's the critical temperature of CO2. So we have kept that as a baseline. So if you see that CO2 is almost around there. On the y-axis, you have the GWP. The y-axis is basically a logarithmic. So we have 1 to 10, 10 to 100, and then 100 to 1000. And then across this chart, there are options, whether it's hydrocarbons like R290, whether these are HFO, pure HFO molecules, or HFO blends like 454C, 454B. Now, if I were to divide the GWP y-axis into 3, anything below 10 is considered ultra low. Anything below 150 of GWP for a refrigerant is considered low GWP. That's like the holy grail we are trying to chase, that if we could for all the application at least reach to 150, and of course if we can go any further down is only beneficial for us. And anything above that is the medium pressure. Then there are these pressure division. Anything below 10, we have considered that as a lower pressure. Between 10 to 40 would be medium pressure or higher pressure. Now we'll talk about the flammability. The green represents non-flammable refrigerant solutions. The yellow and the orange represents A2Ls and A2s. And A3 is basically explosive. So whatever you see there, CO2, whether it's 1336 or 513A, 515B, those are non-flammable solutions. The ones over there in the lower end here, YF is A2L, ZD, 1233ZD is non-flammable, then ZE is A2L. Then we have some others in the medium pressure range as well, whether it's 454, 454C, A, 455A, R290 is A3. What I'm trying to tell you is this, with this graph. It actually shows you the whole landscape. If you want to ever look into it, what that refrigerant means for us, not for its flammability, but for its pressure characteristics also. The bigger thing I'm trying to tell is that if you could see that most of those refrigerants, if you see, are falling towards the lower side of pressure operation. The lower the operating pressure of those refrigerants, the lower the compressor needs to work on this to compress those refrigerants. The lower it needs to compress, to work to compress those refrigerants, the lower energy it will consume, lower electricity energy it will consume. So the general direction of the industry is to move towards lower pressure refrigerants. Because yes, we have this transition which we have to adhere to, but also performance-wise it makes much more sense for us to optimize our systems towards lower pressure operating fluids. So in that regard, I've compared here our existing HFC 410A with our 454B. As compared to 410A, the GWP is like 466, which is one third or even lesser than that, almost 25% of 410A. This actually operates at lesser bar. As I said, because the operating pressures are moving towards lower operating pressures, this is 2.7% lesser pressure. What does it mean? It means in terms of leakages will be lesser, so your scope 1 emissions will be lower. The second thing is, as I said, because the pressure is lesser, your energy efficiency also will gain. The technology readiness. Most of the US market has already moved to it. European market has already moved to it. So 454B is all ready. And then you can have the COP increases, the energy Q delta is almost 18% higher with this. And the last thing is that since you were going to consume lesser energy, it reduces your operating expense also. So this has an economic value as well. If you on the left, if you can see, this is on a Danfoss compressor, which I have compared the working envelope as with 410A. You can see how this red line is much bigger than the blue line of 410A. So whenever you're talking about 410A, if we were designing the system, let's say around 55 condensing, we were much closer to the environment, to the operating envelope if we were, let's say, at around 5 evaporating. But with this, we have a much bigger envelope, so the compressor is not always running on its edges. So that gives a longer life to the compressor. That gives more reliability to your system as well. Similarly, I've compared now commercial chillers. This is a comparison between 134A and 515B or ZE. 515B is the A1 non-flammable version of ZE. As I told you in the previous chart, ZE is mildly flammable. Again, the same kind of a story you can see. GWP is reduced by almost 80% as compared to 134A. The operating pressures are, for once, 134A is a lower operating pressure refrigerant. But even in that case, if you take ZE or 515B, we are another 4 bar lower with 515B and ZE. The same thing, that adds to reduction in leakages. Reduction in leakages, again, your system will not be operating subpar. Charge is lacking in the system, it will not perform optimally. The second thing is, there is a lesser delta K. So if it's a chiller system, and especially if it's water-to-water condenser, your water consumption will reduce. We haven't done detailed studies on this, but our estimation is that this 10K should drive at least 30% lower water consumption at your condenser. Of course, COP increases, that we have spoken about it. It's driven by both its thermodynamic properties and lower operating pressures. And again, that saves you money. On the left, if you see, and this is an interesting chart to see, the black line, this is Eurovent data of all the chillers being produced in Europe by all the Eurovent member suppliers. Any chiller for any cooling capacity, and what we are measuring here in the black line is their seasonal efficiency ratio. You can see the black is the trend line, and the black trend line is somewhere trending around 7. Okay, and it increases as the capacity increases, but let's say at an average of around 7 with 134A based chillers. We have compared those 134A based screw chillers with ZE or 515B based centrifugal chillers. And you can see the red line, which is there, the new equipment's energy efficiency ratio is trending closer to 9. From 7 to 9, that's like 30% increase already. And this is not our data. This is not based on only one equipment. This is the whole data block available with Eurovent. This is their data. Anybody can access it and you can check it. So that's what we are talking about. Now I'll move towards the compression technology and how our refrigerants, HFO refrigerants, are available for most of those. So if you'll see 134, the black line is the existing I've taken there. Then you have an option of 513. The reason I've kept that 513 is that 513 for all practical purpose is a direct drop-in replacement of 134A. Okay. And then on the x-axis, you can see the different sizes of the cooling equipment, starting from 1 kilowatt, the smaller, I won't even call it a condensing unit, a small platform, going up all the way to 20 plus megawatt. The compression technology, whether it's rotary, whether it's scroll, screw, or centrifugal, the HFO technologies options are available for those. So one is your application. So HFO is available for all the applications we are talking about. The other is also the compression. Are the suppliers ready for it? That's the answer for you. One of the bigger things which I also draw from this is, if you see, this is the ZE curve, the light green one. ZE is the most versatile refrigerant which the industry can see, which has less than 1 GWP, and all the other benefits which I spoke about in the previous 4 bar lesser operation, water saving on at least water cooled chillers, and all those things. You may want to ask me that what kind of compression happen at 1 kilowatt with centrifugal compression? That's a good question. But because of this versatility and the performance, we have seen OEMs, compressor OEMs, developing now compressors based on centrifugal technologies. I mean, compressors as big as this, centrifugal compressors as big as this. So the industry has realized it. They know that moving towards lower operating pressures while complying with the lower GWP refrigerant requirements is the way for the industry to go. I'll spend some time on the refrigeration, which Dr. Allah mentioned about that. I'll spend some time on the refrigeration also. I'll skip this one, but this is the one I want to talk about. What we have said, we have taken all the other application sizes of supermarkets or quick service refrigerants, or even large stores or storage warehouses. The color code here says that the dark pink means this is the way that this is how the technology is moving. The lighter pink means this can be done, but this might not be optimized. But based on your system architecture, based on your store architecture, based on your warehouse architecture, this can be considered as well. And you can see that for right now, which is trending in our region and most of the places, is we have an A1 solution to 404A. 404A is amongst the worst GWP producers. It has a GWP around 4,000, which is 134A is 1,500, which is like 3.5 times of that. The other thing is, not only 404A has highest GWP, it's not the best refrigerant in terms of energy efficiency. And that's why we have a drop-in replacement. Existing system can also be done, but if you're designing a new system, that definitely can be done with R448, which is N40, and any application, whether it's condensing unit, whether it's a rack, whether it's self-contained, whether you want to do it semi-centralized, fully centralized. This again is like the ZE of refrigeration industry. As I said, ZE for air conditioning can be applied anywhere for any of the applications. R448, N40 can also be applied for any application, any system design, any store architecture. And not just for new stores, even for retrofitting, you can use it. And that's what we have suggested, that these are the things, whenever you want to have that discussion with any of your clients, any of your own customers, where they want to look into reducing their emissions and also their energy bills of given their existing stores also. This you can achieve by this. Moving to N40 from 404A, and you can check it in any compressor or rack suppliers data selection softwares, improves your energy efficiency. Even for let's say we design our system here for 48 and 43 ambient in Egypt, that's like what, 47, 49 condensing, will improve even for that relatively lower by almost around 12%. 12% for a typical supermarket, we're talking about, given the energy rates going up in Egypt now, probably like $8,000 a month. And if you have, in a year, if you can do 70,000 from one store, and if you have like, I don't know, 50 stores, you're talking about 3.5 million just by this conversion. Existing store, no change. You don't have to stop business. You can do the retrofit probably in 3 nights, maximum 4 nights, and it's done. And from day 0, you start reaping the benefits. As I said, we're going to talk about a little more than just refrigerants and system design. We're also working with a lot of supermarkets to create their digital twin. You might have heard that expression for most of the bigger industrial complexes, but this is a tool which we are developing for our customers in the supermarket arena as well. What does it do? It actually, if you want to do a trial, even before you take a decision and you want to do all the calculations, how will my operating pressures look like? This is my load profile. This is the time number of doors. This is the footfalls I get. We have done this for at least 3 supermarkets right now on a trial basis, and as a POC basis, I would say. And then we were closer to like 2% accuracy based on the data, which it's a big data dump into the system, but the system, the model produces you those details for you. It gives you, it can predict based on this for every given month, what will be your energy bill based on the load profile which you have given us. So the point I'm trying to do is, for us, it's not just about pushing HFOs, selling a box of HFO. It's more about making this transition with the great thing we have in our basket, which is HFO technology, help the industry to move towards those while taking and garnering even more benefits out of it. I don't know if we have people from auto industry, but I'll take a few while talking about the transition happening for auto air conditioning. This is a chart. If you look at this on the left-hand side, as per our latest count in end of 23, like 13 months ago, there are close to 220 million wire-based cars which are on the road. And on the right, you can see all those regulations which are coming in different regions and geographies for auto manufacturers to comply with, to convert from R134A based air conditioning systems to YF-based systems. What does that mean for us? As most of these producers of car producers are in Europe, in Japan, some in China and India, and US, and those are the markets which are already transitioning. We're gonna see, even though we do not have in our region, and region at large, not just Egypt, region at large here, we do not have those regulations coming to us right now. But just because the source markets are transitioning, we're going to see an increase in YF-based cars coming to our region. What does that mean for us? There's going to be an increase in service and maintenance demand of YF. Again, so to support the market, we have every kind of solution the market would need. So if you ever hear about it, if you ever want to have that talk with your customers, even with the regulators, you can see these products are already available in the Egypt market, except for the last one, which we're going to launch soon this year. This is my favorite thing. I have spoken about how we need to comply with regulations, how this transition we should use as an opportunity to actually optimize our system performance. One of the things is money talks. So I've tried to see that whenever that transition happened, if the market didn't plan for it, what happened to the pricing of the phased out material? So if you see these charts, there are two charts here. On the left, which we have shown when the transition from CFCs to SCFCs happened in mid-90s. This is the US data, and the red curve there shows the pricing of CFC12, which was phased out, which was being phased out at that point in time. The market didn't change, but the quota regulations, the amount of refrigerant which could be put into the market was reducing. Demand kept on growing, and hence we saw that spike in price of CFC12 and CFC11 as well. The same thing when under the EU F-gas regulations, we saw the similar thing. The red line there is a 404A price, which goes for refrigeration application. The market took its time, assuming the timelines are longer for them. They didn't change, but the amount of refrigerant, HFC-based refrigerant, we could put in the market was limited, but the demand was growth. So if there is a disparity between demand and supply, that's the red curve you see, how the 410A price has increased. Now after that, the market has stabilized and everything, and that does happen. But during those peak hours, peak time, you can see the price which used to be like 4 euros per kg in 2014 was north of 30 euros per kg. That's like 9 times increase of the pricing. So that's another thing which we need to keep in mind. While we work towards making our energy industry more energy efficient, bringing in new technologies, there is an economic reason, financial reason behind that as well. Okay. I'll just quickly talk about this transition. As I said, this has matured, and these few examples about some of the work which we have done in the region. This is from Middle East region, so I'm not talking about the examples which are from Europe or US where it's been mandated by regulation. In Middle East, this is being done because of all those performance benefits which we spoke about, right? So this is one of the district cooling centrifugal plant running on 1233ZD in Riyadh, in a place called Mist City. That's almost like 10,000 tons of cooling, 23,000 tons of cooling. What we have saved for them in terms of emissions by this transition as compared to 134A, they always had the choice. There was no regulatory requirement right now for them to move. But the customer understood what it means for them if they did not transition, how it could be a big problem for them in coming future. Because the chiller's life, especially a district cooling plant's life, is like 30 years, maybe 40 in some cases. So what we have saved for them is almost around 10,000 tons of emissions over its lifetime. Plus, they don't have to worry about the price variations. They don't have to worry about any whether they will be able to comply when the future regulations will be implemented. So they are future ready right now and reaping the benefits from the day one. Same example, different application, supermarkets. It's a big supermarket chain in Saudi Arabia. They decided that they're going to move away from 404A, as I told, highest GWP, not so good efficiency, to our N40. And this is the saving which they have done annually based on their 30 stores which we converted for them when this study was done. And they are converting more stores as we speak. So this number, both in terms of emissions reduction, is going up for them, and savings on the energy bill is going up for them. Last one. Then we said, okay, these are one examples, each example which we put. How does cumulatively everything put together look for a given country? So we took data of our HFO-based district cooling plants only in running in UAE. This is done end of 2023. There were then 26 plants running, total of around 350,000 tons of cooling. What we assess with that, together with the equipment supplier and the end users, with this transition, by the end user not choosing to move towards 134A, but rather picking up an HFO solution, they have reduced their emissions by 7%. They are running their system much energy efficient by almost 4.8%. And the best thing is, these 26 sites only and 350,000 tons of cooling may be high, but it's not very big in compared to the whole cooling which will be required in UAE. These 26 sites will contribute around 0.5% reduction in the total emissions of UAE during its time. So that's the impact our industry has. We may not be very vocal about it sometimes, but if we put if we see things in pieces, we may not realize it. But when we put the whole puzzle together, this is the impact, just 26 sites. And I can tell you, only in district cooling, they are probably old and new around 100 sites in UAE. We are just 1/4 of that, because the transition started like 5 years ago or so. You imagine if all those 100 sites were there 4 times, this reduction number would have been 2% of that. Before I move further, any questions so far? Because I'm going to change gears a little, but any questions or any comments so far? Okay, so I'll briefly touch upon flammability. It's a deep topic. It needs a lot of detailed discussions, but I want to just touch upon how to assess it, how to look into it. Dr. Allah mentioned that as he sees, A2Ls are the future. Today or tomorrow, the market is moving towards that. So that's what I just want to touch upon it, that how should we see it? Just give me a second, I'll just take some water. So the first of all, it may sound, because it's a change. Our industry, at least I can talk about myself, I've grown up in an industry which was using A1 refrigerants. Anything which was not A1 was only ammonia. That's a different industry for me altogether. I mean, that's a different club. But now if we talk about A2L, it's a change, it could be scary. It may be, and these are chemicals. They have flammability properties. So we have to be aware of it. We should know how to manage them, how to store them, how to stock them, and how to use them when they're in operation, how to service the equipment which are using it. So all those things are necessary. So a little bit of apprehension is required, actually, I would say. But that's what what can we do with that apprehension is the main question. It's just educate ourselves. I'll take a little attempt here, but if you're interested to understand more, we'll be very willing to take deeper discussions on this. Probably we all know this. There are 2 criteria and a refrigerant is judged on. One is toxicity, which is the first letter which we see. And on the horizontal, you see the flammability. So if it's not toxic, or mildly toxic, or low toxicity is A, and high toxicity is B. And if it's not flammable, it becomes 1, mildly flammable 2L, then flammable 2, and 3 is basically explosive. Okay. So when we say a given refrigerant is A1, basically it has low toxicity and it has no flammability. And most of our HFCs fall into that bracket. But as we discussed this morning, the industry is moving away towards A2L. That's the future. And 2L means they have a lower flammability limit. What do we mean by that? Why it's called lower? If you have to judge the flammability of any refrigerant, now I'm talking about flammable refrigerants, not A1s or B1s. There are 4 criteria you look at. One is, what is the chance of flame occurring? So what is their lower flammability limit? What is their upper flammability limit? And I'll talk about this in detail. And if that flame occurs by given chance, what's going to be impact of that flame? Will it travel fast? Will it create a larger explosion? So lower flammability limit is basically the amount of refrigerant you need in your machine room or in a given room, percentage of that refrigerant as compared to the total air in the room. So if its refrigerant is lower than that limit, it will not be flammable. That's the lower flammability limit. Then the upper flammability limit means the amount of refrigerant percentage in that given room compared to the total air in that room. If that percentage is even higher than that limit, there will not be any flame. Once that happens, if within that sweet spot, it's more than the lower but less than the higher, that means there is a chance for the flammability to occur. What you need, if that flammability even, you need, of course, an ignition source for any fire and oxygen for it to perpetuate. But even that fire happens, what will be that energy which will be released by that fire? Is it too high or is it too low? And then that energy also, how far that flame will travel, how fast can that flame travel once that fire has or flame has occurred. These are the four things which we assess this on. There are some other things, how fast the pressure will change, because if going to be a fast pressure change, it's going to be there's going to be an impulse there. If that happens, how much of energy will be produced? What is the heat of combustion? Is there any auto ignition possibility? This is, if you could look at, this is relatively a very simple chart, I tell you. If you look at, it may look at once little complex, but if you look into it, this is the lower flame limit of a given refrigerant. And that's the minimum ignition temperature. That if there is this much amount of refrigerant, below this, there will not be any flame. Above this, if the flame happens, how far the ignition energy will go, how far that ignition energy is required, how much ignition energy is required to make that flame happen. So if you think for propane, acetylene, gasoline, you just need 75 gram per meter cube and probably an ignition temperature of not even 0.1 million joule. That means a small amount of these chemicals with the smallest of ignition source can cause a flame. But when we move towards the right corner, upper corner, you can see the HFOs, you need almost, if not more, at least 5 times more of that refrigerant in the room, and if not more, like probably like 10 million times more energy for you to cause that ignition. And that's why, because this is such a rare phenomenon, that's why that's one of the reasons they're classified as A2Ls. But that's one thing. Even for that matter, if the flame still happens, that somehow a perfect storm builds up, and you have an ignition source that high, and you have the refrigerant concentration within those limits, what happens? How far the flame will travel so that the flame can perpetuate and ignite itself? How much of energy will it release? And you can actually see here all the HFOs on the lower side. That means even if there is any flame by any chance, those rare conditions are met. Even then, there will not be, the flame will not travel faster. That means the fire cannot perpetuate, cannot propagate any further. And whatever flame happens, the energy produced by this wouldn't be any damaging to either to system and not to the technician working on it. As compared to on the extreme upper portion, you can see for the A3s, this is the difference. And that's why they are put into, what I'm trying to tell you is that they may sound flammable because they are. And I'm not trying to say that you don't have to worry about it. All I'm trying to say is that be cognizant of this, that these are mildly flammable refrigerants and they need a different handling, they need a different training, and they need a different way of using them. But we don't have to be afraid of them. With proper training and knowledge, and it goes beyond that, and we have MSDS and everything for all the refrigerants. With proper knowledge and training, it is an issue which can be very well managed. And this is being done. This is being done for many other refrigerants across globes, across other geographies. So it's not something which is unique for our region. As Dr. Allah has said, sooner than later, these refrigerants will make way into systems, into our region. We just need to be prepared for it. So that was my attempt at dispensing any apprehensions you had towards flammability of refrigerants. So if you basically check, I've just put 2, 3. For all proper practical purposes, ZE and YF, in the transportation code, they're actually classified as non-flammable because they know the chances are so little for them to be flammable that they don't want to even carry those. The burning velocity for ZE is 0. That means if those rare conditions are met, you will just have a sparkle. It will not propagate. The flame will not travel. It will just have a sparkle and it's done. We have had a real life case back in Europe where there was a lab and there was an electrical fire in a lab. And we had ZE there in a ISO tank, in a ton tank. A lot of damage was done. Thankfully, no lives were lost. But ZE in that ton tank within the lab was safe. Nothing happened. There were other material which fed on that fire. There was other things which happened. There was other combustible material. Just because ZE was there was no reason for us to be worried about it. Because if we know how to manage, handle and store these refrigerants, it's not an issue anymore. So as I was saying that you can see ZE is actually considered non-flammable for transport This is the summary slide for this. Understand what are the lower limit, flammability limit, and upper flammability limit. How do they impact flammability? What is the concentration is required? And of course, what are the mitigation plan we need to do? Any questions so far? So this is what I have to actually talk about today. So I have just 3 messages if I have to go. A, we have this opportunity when we are working on transition, just not look at only refrigerants and the low GWP, talk about the whole system. And good thing is that with us being here, our partners being here, we have that learning which we have gotten from other markets which we can bring. The technology has matured. The second thing is, the market is moving, there is a change coming. That change can only be tackled if we educate ourselves. Change is sometimes tumultuous, it is chaotic sometimes, and more often than not, it's kind of scary as well. But if we can educate ourselves and you have enough knowledge in the market available, because I've been coming to Egypt for like 18 years now, so I understand this market. There is enough knowledge available for us to educate the industry, the people who are a bit skeptic about any change. And the third thing is, the market is moving towards lower pressure refrigerants. We have to prepare ourselves. We cannot afford to do this thing that we want energy reduction, energy consumption reduction as well, but then we are also talking about higher pressure refrigerants. That's it. And the last thing is flammability. Even for R32, that's not our product, but even for R32, I have laid it out there. If somebody has any questions about that, please reach out to us. Please talk to us. We'll be more than willing to make it easier for you to understand. We have much more, way smarter and more knowledgeable people than I in my organization who are the subject matter expert. We can connect you with them and they can make it much easier for you to understand that. So that would be it from me. Thank you very much. Any questions? Okay. Then if I could invite Mr. Akmal to just give the vote of thanks for everybody. Thank you very much.
السلام عليكم. دايما بنبقى حريصين على ان احنا نقدم الجديد دايما في وسائط التبريد، وطبعا بنستعين بالخبراء زي دكتور علاء دايما بيبقى مرشدنا في حاجه زي كده، وطبعا بحضراتكم، وكان تشريفكم لينا من دواعي سرورنا. Thank you for Amanda and all the team of Honeywell. اتمنى ان احنا نكون عند حسن ظنكم. شكرا لحضراتكم.
Thank you, sir. So we can now disperse. The lunch is being served downstairs in La Palmera restaurant. If you just come out of the lifts or if you go down the stairs, you will see it, you turn left and it's on the left. And if we can make our way towards that. But thank you very much for everybody giving your time to us. Thank you. I hope this session was informative. And we will like to keep this dialogue continued. Thank you very much.